Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 37, part C. We are going to finish up the discussion on continuous bivariate distributions. So last time so far, we have introduced the joint range of x and y, which again is extremely important in solving the problems, as we're going to see in this example today, in this video. We talked about the joint PDF, the properties of the joint PDF, marginal distributions, independence, and our example today will cover correlation and regression. So let's get started with this example. And as I mentioned last time, the properties for covariance and correlation that apply to the discrete case also apply to the continuous case. The only difference is that our expectations now involve integrals instead of sums. So example 3 here, we're going to let x and y have the joint PDF f of xy equals 1. And x is between, or y is between x and x plus 1, x is between 0 and 1. We want to find the marginals, the means, the expected value of x squared and y squared. We want to find the variances of x and y, the covariance between x and y, the correlation, and also we want to find the equation y equals a plus bx, the linear association that exists when rho is equal to 1 or negative 1. All right, so first step, draw the joint range of x and y. So x here, y here. In this case, y is between x and x plus 1. That means y equals x, and so y is between that and y equals x plus 1. So two lines. And so I have given us these lines. Again, there's a less than, not a less than or equal to, so the lines are dotted. And so here is our y equals x, and the top line here, y equals x plus 1. I'm also going to express these in terms of x because I will need them. As you can see, I have put in the equation of this line, x equals 1, this line, x equals 0, and I will put in x equals y minus 1 and x equals y as alternate ways of expressing those two lines. Now, when you look at this, if you were integrating with respect to y, you're going up. So you're going straight up here. I can't draw a straight line, but if I could, this would be a straight line. I'm going from y equals x to y equals x plus 1. And that is true across the whole space, a whole range of x from 0 to 1. That's fine. But when I start looking at this as an integral with respect to x, if y is between 0 and 1, I'm moving between x equals 0 and x equals y. However, if y is between 1 and 2, I'm moving between the lines y equals x plus 1, or I'm sorry, x equals y minus 1 and x equals 1. So these are different. So I'm going to have to make a piecewise integration with respect to x, in the direction of x. All right, so it has to be, so the bottom portion and the top portion will be integrated separately in order to get the answers. All right, so we're going to start with the marginal distributions. And we're going to use the marginal distributions to find all these other quantities that we can. So mean of x and y, ex squared, ey squared, sigma x squared, sigma y squared. The only ones we can't do that with are the last three, the covariance, the correlation, and the regression line. All right? But when I make a test, I budget you time to do things the efficient way. And the efficient way in this case is to find the marginal distribution and use it in the next calculations. Why? Because if I have to, if I want to find the mean using the joint PDF, I have two integrals to do. If I can do that integration once up here for the x for the y, I'm sorry, for the direction of y, I can do this integral once, and then I already have it done. So the only thing that's left to do when I get the marginal of x is integrate in the direction of x. So I'm saving time, I'm saving that integration, and lowering the chance that I make a mistake. All right. But using both is a good way to check your work if you have the time. If you don't have the time, I suggest that you use the marginal. So let's find the marginal of x. We're going to integrate in the direction of y. So again, when we integrate this in the direction of y, we have the same integral for we have the same integral all the way across x. So we're going from in direction of y equals x to y equals x plus 1. All right. And so the PDF, the joint PDF is 1. I want to comment that this PDF here is the uniform. This is a continuous uniform, but it's a continuous bivariate uniform. And remember that we talked about the time before last that this is that we have a plane, this xy plane down here for our space of x and y. And this, the PDF, can be thought of as the z direction, or coming out of the plane or out of the paper towards us, and that height is constant at 1, and that's what makes it a uniform bivariate, is that z direction, or the direction out of the plane of x and y perpendicular to that plane, is constant. Okay, so we're taking the derivative with respect to y. We get y, and we're going from y equals x to y equals x plus 1. We substitute in x plus 1 minus, of course, x, and we end up with 1. So again, what we're looking for the expression of the marginal is both the value of it and the range of x in this case, since it's the marginal of x. X is the only thing that should be left in there. If you still have a y, then something is wrong. You haven't integrated it correctly or simplified it correctly. Okay, so now we find the marginal of y, and again I'm going to use I have to use the joint PDF to find the marginal, of course. I'm integrating with respect to x, and x is simply from 0 to 1. It was expressed independently, and when I look at the picture, certainly it looks independent, but when I'm integrating with respect to x, again, I have to do two pieces of this. So I end up with a piecewise function. When y is between 0 and 1, I'm integrating between 0 and y, x equals 0 to x equals y. When y is between 1 and 2, I'm integrating from y minus 1 to 1. So x equals y minus 1 to x equals 1, which we can see in our picture up here. And so I get x for both, but then my limits of integration are different for each case, and so I end up with y here and 2 minus y here. So what I'm looking for the expression of this marginal is what I've put a box around here. So that's what I'm looking for. It's piecewise, okay? So I want this piecewise function. Now I've written it backwards to save space, but you know how to write it. But I would certainly accept it if it's written this way. That's fine on a test. Now, I need to find the mean of x, the marginal mean of x. Again, I could do this with the joint PDF, but that is not efficient, so I won't. I'm going to use the marginal. I've already done the work of integrating across y. Why not take advantage of that? So I need x times f of x to get the expected value of x, which is the mean. And remember that the marginal f of x is 1, so I'm integrating x between 0 and 1. I have 1/2 x squared, which simplifies to 1/2 when I plug in 1 and 0. Now we find the marginal mean of y, and again we're going to use the marginal distribution of y because it's simpler, from 0 to 2. So again, when I'm integrating in the y direction, I only have one integral that I have to do. It's the same all the way across for all values of x between 0 and 1. And so I Okay, so I'm going for, actually I have y between 0 and 2, and oh yeah, so I'm integrating with respect to y. I'm sorry, I was thinking of x. So I'm integrating with respect to y, but I have to use the marginal. And so, unfortunately, the marginal is in two pieces. I have, it's a piecewise function, so I have to use both pieces. So here's the first piece, and here's the second piece, and I add them to get the mean. You can't have a piecewise mean, so you want to add the different portions together. So f of y between 0 and 1 is y, and f of y between 1 and 2 is 2 minus y. I combine those, and I combine the terms, and I get y squared dy for the first integral and 2y minus y squared for the second. You cannot combine those because you have different limits of integration. And so we integrate that. We get 1/3 y cubed for the first part between 0 and 1, y squared minus 1/3 y cubed for the second part between 1 and 2. I plug in. Please look through this and make sure you understand what was done, because it is important to get the right answer. And we end up with the marginal mean of y is 1, so different than the marginal mean of x, which was 1/2. Ex squared, I'm going to use x squared f of x, and between 0 and 1, and I plug f of x as 1, so I've got the integral of x squared is 1/3 x cubed from 0 to 1, which leaves me with 1/3. Okay? And I do the same with the expected value of y squared, but again, this is in pieces. The marginal of y is in pieces, so I have to do a piecewise integration here. So two pieces, I have to add them together. And please look through this and make sure that you can understand the details. Make sure that you can work through this and get the correct answer, because it's very important that you do so. So I got 7/6 for that. I get 1/3 for ex squared. Now I find the variance using those two quantities. And so 1/3 minus 1/2 squared gives me 1/3 minus 1/4, which is 1/12 for the variance of x. And 7/6 minus 1 squared for the expression of y gives me 1/6 for the variance of y. So the variance of y is twice the variance of x, because 1/6 is 2/12, so it's twice as large. Now we want to find the covariance of x and y. Again, I want you to do this in pieces. I want you to find e of xy first, and then use this formula to find the covariance. Again, this is a less chance of error, so I strongly suggest it. All right, so I have xy times f of xy dy dx. I'm doing dy first because I have to define it in terms of x. And so I'm going to do my integral with respect to y. So that will leave me with 1/2. So inside this integral, I have 1/2 xy squared, and y is going from x to x minus 1, or x plus 1. All right. And so I end up with this expression here, plugging in, and then I simplify here, and, because I still have, so I have this 1/2 x, and so I really only have to do, this is 1/2 x, so this is y, and I'm substituting in x plus 1, or y squared, so x plus 1 squared minus x squared, since that 1/2 x factors out, if you will, from the whole thing. This is a simpler way of calculating it. I expand what's in there, x squared plus 2x plus 1 minus x squared, so these cancel out. I'm left with x squared plus 1/2 x dx. Integrate that. 1/3 x cubed plus 1/4 x squared. 0 to 1 is 1/3 plus 1/4. It gives me 7/12. So my covariance is e of xy times minus e of x times e of y. And that's 7/12 minus ex, which is 1/2, ey, which is 1. And so that ends up giving me 1/12 for my covariance. Rho is the covariance of x and y divided by the standard deviation. So don't forget your square root here. I take a half times a sixth, and my covariance is 1/12. So I can simplify this, and I get square root of 2 over 2, which is approximately 0.707. We always do this to 3 decimal places. Now we want to find the least squares regression line. So I do not need the hat here. I just need y equals a plus bx. We need the hat when we are estimating these values, and we're not estimating them, we're calculating them using the population quantity. So this is the actual line, the population line at rho equals 1 or negative 1. Okay, so b is going to be the covariance divided by the variance of x. And so these turn out to be the same value, 1/12. So b is equal to 1 here. And then I have a is mu y minus b times mu x. So I substitute in for mu y, which was 1, b was 1, and mu x was a half, and I get 1/2 for a. So my equation is, if you remember, y equals a plus bx. A was equal to 1/2, b was equal to 1, x, so we get 1/2 plus x, and that is our least squares, or best fitting regression line, or equation, regression equation, either one. All right, so that's it for this section. Please don't forget to scan and upload your lecture notes before midnight, the date listed in the course calendar. If you have questions, please come to virtual office hours. If you can't do that, then of course you're more than welcome to email me, but when you do so, I need 2 things from you. I need a picture of your work, and I need a picture of the problem so that I can quickly help you and respond by email. Otherwise, it will have to wait until I get access to the problem if I don't have access to it. So I hope you'll do that if you need help, and I hope you'll stay safe, and we hope to see you next time.